Based on the scatter plot, describe the relationship between mass and length in context. So if it asks you to interpret a relationship, strength, direction, and form, strong positive linear association between the two variables in the context of the question. That's your part A. Then part B gave you the equation and asked you to identify and interpret the slope. So first of all, you needed to identify it, which was 6.086. And then make sure you have the word predicted in that interpretation of slope. Bullfrog's mass is predicted to increase by that amount for every 1 millimeter increase in its length. Or you can flip the direction that you interpret that, but that's your interpretation of slope. Then it asks you to interpret r squared. There's your interpretation of r squared in the context of the question. Percent of the variation in y can be explained or can be accounted for by this least squares regression line. Percent of variation in y that can be explained by the least squares regression line. That's part C. Then part D. Part D asked you about residuals. So first off, which one had the largest absolute value residual? That means we don't care about whether it's positive or negative. We just care about the number. Which one has the largest number as its residual? And the one that has the largest number as its residual is this one right here. That's the residual that has the largest, even though it's negative, the largest absolute value residual is that one because it's the farthest from the regression line. So that's the point you should have identified that it was. And then it asked, do we over or underestimate at that point? And honestly, you didn't even need to know about residuals to be able to answer that part, because you can just look at the line and say, well, the line is going to overestimate it because it's above the point. So, but explaining in terms of residuals, it overestimates the mass because the residual is negative. Residual is negative means that the observed is below the predicted. Observed is lower than the predicted. That means that our prediction is too high, so we are overestimating the mass. Now it's question 1. Number 2, this is your question about experimental design. So we're identifying the treatments, we're going to talk about matched pairs, and we're going to talk about how that matched pairs process gets carried out. So first of all, what are the treatments? Your treatments, the two treatments are the new drug and the placebo. The experimental units, you can either say that they're the people. Each person is an experimental unit, is a subject. You can also say that the 36 pairs, they would probably take that as well. Response variable, what are we measuring about these people? What are we seeing how this treatment affects? Well, the improvement of the acne severity on that scale. And we talked about this. We've talked about this before. When you say the response variable, you should define it in a way that you can see and track how it's getting measured. Okay, then part B, we're using a matched pairs design. Hopefully we're doing decent on this because we talked a lot about matched pairs design. There should be an obvious way to pair up the data. And in this case, the obvious way to pair up the data is what? The twins, the identical twins. So because the identical twins are most similar to each other, we can more directly compare them to each other. That's the idea behind part B. That's why we're using a matched pairs design. If we were using a completely randomized design, we would just have this group of 36, this random group of 36 versus this random group of 36. Versus if we have a matched pairs design, then we have one of the twins getting one treatment and the other twin getting the other treatment, and we can directly compare the two. And how are we going to do that? Is that within each pair, you should number one of them twin 1 and one of them twin 2, and some kind of random process to randomly select which one gets the new drug and which one gets a placebo. and then you're going to compare between those two groups. And you can describe whichever random process. You could have a slip of paper numbered 1 and 2. You can have like a red chip and a blue chip in a bag. You could flip a coin to decide which one, since we just have 2 people. Random number generator, rolling a die, just making sure you're assigning what outcome goes with what. It's probability time. It's time for your probability question here. So first off, normally distributed. First thing you should do is to draw a picture. There's your normal distribution. And we're looking for the underfilling. These are the different ways you can show a normal distribution. Here's kind of the standard notation for the normal distribution. Here's the normal curve with the mean and standard deviation labeled. Here's calculation of the z-score. Any of these show that we're looking at a normal distribution. And we're looking at the probability that they're underfilling, so the probability should be that they're less than that amount. That should be, I put in the normal CDF commands that are there just so that you know. But regardless of how you did it or how you showed it, this is what you should have gotten for that probability. So that's your normal CDF. That's part A. Part B. We want the probability that the crate will be rejected. We have 10 of these. We have 10 bottles in the crate, and we're looking at how many of them. We're looking at how many of them are underfilled. Therefore, what kind of distribution? Binomial is right. That is a binomial distribution. We have our set number of trials, which is n. That's 10. There's 10 times that we are repeating the process. And probability of the thing happening is the 0.0062 that whatever answer we found in part A. That's your probability of it happening. And then in the next part, it asks you to actually do the probability. At least 2 of them, the opposite of at least 2 is less than or equal to 1. So that's what should go in that binomial CDF, or if you wrote out the whole binomial formula, that's what you would write. Either way, that's the probability that you should get. Part C, you do not need part B to do part C. Part C gives you a new distribution with this mean and the standard deviation, and basically asks you to compare it with the distribution in part A. Should we change it to this new one? Would this be a better, the lower center but a smaller spread? Or should we stick with our original programming of how they're filled? And based on probability calculation, this one is more likely to underfill. So that means that you should probably stick with the original programming so that we have a lower chance of the bottles being underfilled. All right, this is your 95% confidence interval. This was a pretty straightforward confidence interval because this is a 1 proportion Z interval for 1 proportion. Here's your P hat and N that you're going to be using. Here's your random, here's your normal, and here's your independent. The random should be the N times P and N times 1 minus P hat are both at least 10. And make sure you define your variable up in step 1. Then, here's formula, plug in the numbers, answer. That's your confidence interval. We are 95% confident that the actual proportion who would respond that they use a video streaming service is between these 2 values. That's your confidence interval. There's part A.
I remember my calculator was messed up, and every single test I had to do, I had to do it by hand.
So that most common error, by the way, is that when you put your X and N, it should be a whole number. You don't want to put a decimal in for the X and the N. Otherwise, it's going to give you an error.
I did that at first, and then it gave me an error. Just round it.
here's that x, you round it up, there's the n. That I actually made a note of that. That's what should go in the calculator.
I was like, okay.
Did you make up an interval and well, no, you did the interval and okay.
I just don't understand that.
So part B then asked you, based on this confidence interval, is there enough evidence that the proportion is not 0.5? You did not need to do a whole new 4-step process on this one. The idea that they were looking for is, based on this confidence interval, does this confidence interval include 0.5? No, it doesn't. Therefore, we would reject the null hypothesis and conclude there is enough evidence that the proportion is not 0.5. Let's rip the band-aid off. Let's do number 5. Okay. Number 5, I think, was the toughest. That being said, I think that part A was pretty doable, was pretty gettable. Determine and compare the medians. So hopefully you actually compared them, used comparison language here. So on part A, here were where the 2 medians should have been. There were 13 in one group, so it should be at the 7th data point. That's where the middle value should have been, and that was at 7 on the dot plot. And then the median of the other group, since there were 12 of them, you want halfway between the 6th and the 7th. And so we average them together and we get 0. So the median of this one is higher. Median of the dark chocolate is higher than the median of the white chocolate. Part B, just because there is a difference in the samples doesn't mean that we can automatically reject the null hypothesis and conclude that there is a difference. That's why the hypothesis test exists, because one of the possibilities is that we just happen to get a sample where that difference exists. So that's the idea of part B that they're trying to get to, is the idea, this is what your null hypothesis says. When you say the null hypothesis is that the mean difference is 0, what you're saying is, here's the sample that I got. It might be that there isn't a difference, and I just happen to get that from sampling variability. So that's the idea on part B. And then the p-value is the probability if that null hypothesis were true, if there is no difference, what is the probability I get a sample that extreme, which is what part C was getting at. So here are a bunch of different means that you could have. So based on all these means, is there enough evidence of a difference? All you had to do here was say, well, 5.66 was my difference. So the 5.66 would lie here. Well, actually, more like up here. So that 5.66 difference happens up here. So how often is there that much of a difference? Is there that much of an increase? Well, it's just in these 3 values. Out of all 120 trials, the probability I get a sample that extreme is 3 of those samples out of the 120. That's my p-value, which is less than my alpha level. Reject the null hypothesis. So a lot of these questions, when back in chapter like 9 on like the first section, when it was like interpret the p-value in the context of this question, not rejecting or failing to reject, but like, what does the p-value mean? What does the p-value tell you? That's the idea that this question was getting at. Question 6. This question overall was about the idea of Simpson's paradox, which is that overall proportions can be shown to be misleading when you break them down into their smaller groups. So that's the idea that this question is getting at. And again, like we talked about, and on those question 6s, you can kind of get to the end of the problem and kind of see where they're going with this question. Is that this conclusion might be in contradiction with the conclusion in part A, and discovering why that is. And it really takes you along the steps, along the path to get there. So let's start with just plain old part A. So to fill out this table, successful versus unsuccessful, relative frequencies, we take these proportions. There's your proportions, successful and unsuccessful, in the table. And based on those proportions, clinic A appears to be more successful because a higher proportion of them were successful than clinic B. That's your part A. What a statistically significant result. Allow the researchers to conclude that the treatments caused a higher percentage. So was there causation? Well, to establish causation, you need an experiment. So this was not an experiment. Therefore, we would not be able to establish causation because this was not an experiment. The subjects would need to be assigned to randomly assigned to one of the two clinics in order to make a conclusion about whether one of them caused the other to happen, to eliminate any confounding variables. Here's your designs. For the record, I had to read this like 4 times to figure out what the difference was between what this was asking and what this was asking.
Was it not the same question?
So it was not the same question. This one was asking which allergy is treated more successfully. So you're looking at the success rates here and the success percentages. Over here, it's asking which allergy severity is more likely to be treated. In other words, between mild and severe, which one is treated more often at Clinic A, which one is treated more often at Clinic B. So that's what the wording of the question. I thought that was fairly unclear wording because I had to read it a bunch of times to understand what they were asking. But you can see which one's treated more successfully at both of them. The mild allergies were treated more successfully, and here's the proportions to break that down and compare. And then the next part, in Clinic A, mild allergies were treated more often, and in Clinic B, the severe allergies are treated more often. And you can see that in this graphical layout, that a lot more mild than severe. This one has a lot more severe than mild. So their conclusion was that Clinic B was better, was more successful at treating the mild allergies and the severe allergies. However, up here, didn't we conclude that Clinic A was more successful overall? This is Simpson's paradox. This is Simpson's paradox, which is that initial conclusion may have been misleading. The Clinic A was more successful, and the difference in the success rates might have been due to the fact that Clinic B had a lot more severe cases than Clinic A. So because of that higher rate of severe cases, it's making it look like Clinic B is less successful, when in reality there's another variable of what kind of allergies are being treated that is happening, that is at play here. Because you see that within the groups, between the two, Clinic B is more successful at treating mild allergies. Clinic B is also more successful at treating severe allergies. So that difference, that Clinic A is more successful overall, could just be due to the fact that Clinic B is having to take those more severe cases, probably because they're the more successful clinic within each group. So someone with severe allergies may want to go to the clinic that treats those severe allergies better. So it draws more people in, therefore they get more severe cases, therefore their overall proportion goes down, and it makes the overall proportion look worse than it is. So any of the above that I just said for part D is the idea that they're getting at there. And Simpson's paradox, it got cut off here, but Simpson's paradox is the name of that idea.